Okay. So Henrietta Swan Leavitt was born in 1868 and died in 1921. We have 52 of her notebooks in the Project PHaEDRA collection. And for anyone who's new to the project, what the PHaEDRA collection is the notebooks of many astronomers who worked at the Harvard College Observatory over the years. And all of Henrietta Swan Leavitt's notebooks have been transcribed in the Star Notes project, meaning that we have all of the plate numbers in that project. I don't think that all have been transcribed in the Smithsonian project, so we're still working on those. She's now known best for what we call Leavitt's law. This was her major discovery of something called the period luminosity relationship for Cepheid variable stars. And I'm going to be talking more about that, hopefully explaining it so that you understand it if you have never heard of this before, because it did change astronomy. It was a really, really major discovery that Leavitt made. She originally attended Oberlin College in Ohio before transferring to Harvard, and this was for her undergraduate degree. This was right around the period where it was the last years of it being called the Harvard Annex, which was what women were admitted to at Harvard College. Right after I think Leavitt graduated, it became renamed Radcliffe College, and then it was Radcliffe College for about 60 years or something like that before Harvard became fully co-ed. She started, or she gained an interest in astronomy at this time while she was undergrad at Harvard, and she took a course on it and got an A-, the records show. And then right after graduating, she started working at the Harvard College Observatory under the director Pickering. And this was on a volunteer basis. At the time, the Harvard College Observatory, I think, was sort of cash-strapped. And so if they could get people to volunteer their time to work on projects, they would accept that. And Leavitt was from some means, so she could support herself while volunteering at the observatory. And this was the earliest notebooks that we have from her are from this period, and she was already starting work on variable stars. Then after a couple of years, she left to travel, and she went to Europe and then back to her home in Wisconsin. And unfortunately, at this time, it was the first time she got ill and started to lose her hearing during this time. Then there was a series of letters we have where she's living with her family in Wisconsin between her and Pickering, who again was the director, Edward Pickering, where she's talking about wanting to come back and working at the observatory. But she actually says she has this strong interest in astronomy, but she wanted to work in an observatory with a better climate than Boston had, because there was some thought that maybe the cold weather had some effect on her hearing. But Pickering sort of suggested in these letters between them, no, there's no other observatory that would do this kind of work. We're the best in the world looking at stars, and you're so great at it. Why don't I pay you 30 cents per hour? This was a 5-cent increase over what they were paying at the time, which was 25 cents per hour. And she said, well, that would be fine. And then she came in 1902 and started working full-time at the observatory as a Harvard computer, which is Pickering would hire women to make these calculations based on the glass plates, and they were called the Harvard computers. And this period, right after she came back to Cambridge, from 1904 to 1908 was when she started working in earnest on variable stars in the Magellanic Clouds. And so let me explain a couple things here. What a variable star is it just means that its brightness fluctuates over time. And so we call if on September 10th, it was this bright, and then on September 11th, it was dimmer, and then on September 12th, it was brighter again, we call that the period. So how often it's fluctuating in brightness is the period. And it's usually measured in days, but some stars fluctuate really fast. They have a fast period, and some stars fluctuate a lot slower. We now know actually from the glass plates that some variable stars fluctuate over decades. So they have really, really long periods. And Leavitt became interested in the Magellanic Clouds because there were so many variables in the Magellanic Clouds. And at the time, we didn't know exactly what the clouds were. They were only visible from the southern hemisphere. So these were plates that were, there were photographs from the Harvard Observatory in Arequipa, Peru, and brought back up to Cambridge, where then Leavitt would very meticulously look at these variable stars and make notes about them. I got to actually help someone who did work at the library named Peggy on a little project to try to understand how Leavitt did this work. And we made this brief video, which I'll show you now.
Leavitt identified variable stars by gathering images of a section of sky from different nights and overlaying a negative in turn on the positive print from a different night. Stars of constant brightness neutralize the differences between their positive and negative images to look gray, while variables showed with black or white rings to the practiced eye where they did not completely overlap.
Okay, so I know that was quick, so I'll talk about it a little bit more. Here's what perhaps what Leavitt would see when she was putting one negative plate against a positive plate. And basically what she was looking at is these were two photographs taken on different nights, and they would compare the brightness basically just on the size of the star in the photographic emulsion. So a star that got brighter would spread out more and it would become bigger. And so if a star's brightness was constant, basically when you looked at it on multiple nights, it would just, you wouldn't see any ring around that star because the size of the star wouldn't change. And these photographs were taken with the exact same exposure time so that they could be sort of a good guide for how much the star is changing over time. And then if the star had a ring around it, like these ones, then that would suggest that that star is getting brighter and dimmer from day to day. And so she would take she would be looking at all of these different glass plates taken over many nights of the Magellanic Cloud and measuring how the brightness changed and keeping track of that in the notebook. So if you look at the notebooks of Leavitt, you'll see all of these tables of how the brightness is changing for individual stars in the cloud. And in 1908, she did a first publication on this work called 1,777 Variables in the Magellanic Clouds. And there's a key sentence in this 20-page article, which is, "It is worthy of notice that in table 6, the brighter variables have the longer periods." And that one sentence statement would go on to be really, really important. The way I think she's phrasing it here, "it's worthy of notice," suggests that it's maybe not, they don't know how scientifically relevant it is yet. And so she's just sort of saying, I think this is interesting, but we're not sure yet. Because, and the reason they weren't sure yet is because they were working with a fairly small set of stars to make this comparison and looking at the table. And so one thing that she wanted to do was return to her work on the variables in the Magellanic Clouds using more photographs and more intense research of looking at all these plates and trying to figure out, is there really this pattern here? And so I'm going to skip over a number of years where she had more illnesses and was also taking care of dying parents, but she came back to Cambridge and in 1912 published another paper called Periods of 25 Variable Stars in the Small Magellanic Cloud. And in this paper, she published this graph here, figure 2, that shows you can draw this straight line basically. And what this straight line indicates is that if it's a dimmer star, it's going to have a faster period, meaning it's going to vary in brightness quicker. And if it's a brighter star, it's going to have a longer period, meaning that it takes more days for it to go from its brightest point to its dimmest point back to its brightest point. And so this was really interesting. People were like, oh, this could be something pretty major. And the next year, another astronomer and this is where I'm going to try to explain all of this, but I'll note that I'm not an astronomer, I'm a librarian, so give me a little bit of leeway here, but hopefully I can explain how this discovery was really important. Another astronomer named Hertzsprung, who was Danish, he found the same kind of variable stars, but much closer to us. And when a star is much closer to us, we can call it a foreground star. We can measure its distance with something called trigonometric parallax. And the way that parallax works is we know the distance from Earth to the sun. And so and we know that Earth is rotating around the sun. And so if we wait 6 months, we're on the opposite side of the sun. And so we know that distance. And then we can look at how much this foreground star has shifted, and then we know the angle that it's shifted in the sky. So it's like we call this in arc seconds, and so we can say, okay, that star has shifted a half of an arc second, as an example. Then from that, using trigonometry, we can actually calculate the distance of a faraway star. So this is called parallax. And what's important about that is then if we know the distance of a Cepheid variable that's much closer to us, we can then use this calculation of Leavitts of how the brightness changes to know how far away, really, really far away Cepheid variables are. And because from our vantage point, the Magellanic Clouds are just impossibly far away, we can now use that as what we call standard candle. So we can use this much closer star, we can then calibrate with that and know how far away a really far off galaxy is. And this was used later by Hubble and Andromeda to show that not only are these other galaxies really, really far away, but the universe is expanding. And Hubble, would always give credit to Leavitt's work and say that without her work, his work wouldn't have been possible, and said that Leavitt should have been awarded the Nobel Prize. We actually know from the Nobel Prize Committee that some people actually did nominate Leavitt for the Nobel Prize because her work was recognized just at the very end of her own lifetime, but that they didn't know that she had already died, because she did die at an early age of 53 from stomach cancer. So it's likely she would have won the Nobel Prize in astronomy or physics for this discovery, because it led to so much more about our understanding of the universe. The idea that there are other galaxies and they're really far away, and that the universe is expanding, and all of these things that modern astronomy is all about. So hopefully this has excited you a little bit about the work that Leavitt did. And this is a picture of Sam and I with one of her notebooks where she was studying the brightness of variables in the Magellanic Cloud. And here's a close-up of it. And you can see there's tables of the brightness of different stars, and there's like a little taped in section because the notebooks are really tied to these glass plates where they would also make notes. And so the goal of Star Notes is to make all of these connections more permanent digitally, so that we can have the digital scans of the notebooks, the digital scans of the plates, and know exactly how all of these connections happened. All right, so that's the end of my part here. I'll just mention there is some good research you can do if this interested you in Leavitt, including a biography by George Johnson called Miss Leavitt's Stars: The Untold Story of the Woman Who Discovered How to Measure the Universe. And there's also a shorter book by Dorrit Hoffleit called Women in the History of Variable Star Astronomy. And Dorrit Hoffleit is who Sam is going to tell you about next.
Thanks, Nico. So I'm just gonna, let's see, share my screen. Okay, that looks good. Okay, so as Nico mentioned, I'm gonna be talking today about Dorrit Hoffleit, who was another computer at the observatory. Hoffleit's notebooks have also all been looked through on the Zooniverse platform, and so we're super excited about that. However, we do still have some notebooks of hers that are going to go up on the Transcription Center, the Smithsonian Transcription Center, and so we just kind of wanted to give some biography and background about her. So her full name is Ellen Dorrit Hoffleit, and she was born in 1909 in Alabama, and 1907 in Alabama, and she died in 2007 in New Haven, Connecticut. So she did live to be 100, and that's a picture of her on the left there. I'm just going to talk a little bit about her education background. So she studied math in undergrad. Her family moved from Alabama to the Cambridge area. I believe her brother went to Harvard, and so she enrolled in Radcliffe College, which, as Nico mentioned, it was the Harvard Annex, and then eventually became Radcliffe College, where women studied. So she got her undergrad degree in 1928, and then went on to receive her PhD from Radcliffe also in 1938. And her PhD dissertation was titled "On the Spectroscopic Determination of Absolute Magnitudes with an Application to Southern Stars of Types Later than A." So that's the research that she did for her PhD. She was officially hired as an astronomer at Harvard in 1948, which, like, she was given the official title of astronomer, but she worked for Harvard for a long time before that. She worked as a computer during her PhD and in the years between finishing her PhD and, working as an official astronomer at Harvard. And so on the right there is her yearbook photo. So in 1928, as I said, she started working as a computer. She earned 40 cents an hour for her work. On her application to the American Association of Variable Star Observers, which is kind of a group for astronomers who study variable stars, she applied when she was 23, and she listed her experience with astronomy and variable stars as examining photographic plates to find and determine periods for variable stars, which was a reference to her work at Harvard. So much like Leavitt, she also did a lot of work on variable stars, like many of the computers did at Harvard. And she once stated, she had this really, really long career in astronomy, and so she was talking about her career, and she once said that the Harvard plate stacks are the only place in the wide world where I belong. It's still true. So eventually, as I mentioned, she worked as an astronomer at Harvard, but then she eventually moved on to work at Yale. So she worked at Yale from 1956 until her retirement. And so even though she was retired, she continued doing research into her 90s. She was really, really passionate about her work and dedicated so much of her life to it that she did not want to stop doing research once she officially retired. And there's also a scholarship at Yale called the Dorrit Hoffleit Undergraduate Research Scholarship that goes to an undergraduate science major every year. And that's a picture of her on the right, taken at the Maria Mitchell Observatory, which I'll talk a little bit about later. But first, I want to show you all these 2 pages that were found in our PHaEDRA notebooks. And it's actually a letter that was added into the notebooks later. Like, sometimes we get a lot of ephemera that's kind of added into the notebooks, like just, stuck in the book later on in time. And so this letter's from 1994, and it's signed Dorrit at the bottom on the right there. It's, on Yale letterhead, and Hoffleit sent this letter when she was 87. So clearly she was still doing a lot of research and a lot of work, into her late 80s, early 90s. So this was, to me, it's such a neat thing to be able to get to see. So as I mentioned, I also mentioned the Maria Mitchell Observatory on Nantucket, which Nantucket is an island, for those who aren't familiar with, New England geography. But so she she was all, on top of being an astronomer, a professor at Yale, she was also the director of the Maria Mitchell Observatory. And she was the director from 1957 to 1978. She was the second director, the first being Margaret Harwood, which is pretty cool because Harwood was also a computer at Harvard. And so the fact that Hoffleit divided her time between Yale and, being the director of this observatory is, really astounding, because she had a full appointment at Yale. Like, she, was a full professor at Yale and teaching classes and, doing all these things. But she split her time. She did 6 months on Nantucket and then 6 months in New Haven, which is, where Yale is. So she was so passionate about her work and so dedicated. She really was just so busy, I imagine. She, at the Maria Mitchell Observatory, she started a summer research program for undergraduates. From my understanding, she really loved working with undergraduates. I think at Yale, she taught like an astronomy 101, like the intro, the most introductory course to astronomy, because she really, really loved, working with young folks and encouraging them to pursue astronomy. And I think that was one of her passions. So she won. She was given a lot of awards during her life for her achievements. She was given the George Van Brysbroek Prize from the American Astronomical Society, AAS, for lifetime achievement in astronomy. She was inducted into the Connecticut Women's Hall of Fame in 1998. That's what the image on the right there is. She got the Caroline Willoughby Prize from Radcliffe College, and she has a minor planet named after her, which is pretty cool. So as Nico mentioned, she published the Women in the History of Variable Star Astronomy, which, talks about, all these women who contributed to the field. She also has a numerous amount of, she has a ton of other books and publications. She, as a professor, as an astronomer, she published tons and tons of papers, but, most notably, she was the author of the Bright Star Catalog, the co-author of the General Catalog of Trigonometric Stellar Parallaxes. She wrote for Sky and Telescope magazine. She wrote a history of astronomy at Yale, publication, and she also wrote an autobiography called Misfortunes as Blessings in Disguise. So I'm just going to show you kind of some brief other findings in the Hoffleit notebooks, because I think Hoffleit in particular has some really, really fascinating notebooks. So this is an example of spectra lines. So basically, some of the computers, along with studying variable stars, they studied stellar spectra. And basically, how the spectra works is that it breaks up the stars' colors, breaks the colors apart through a prism, right? And those are the absorption lines that you're seeing kind of on, those 4 lines, those 4 kind of sections there. And so you can like kind of identify different chemicals that way and stuff like that. And so I think this is a really neat example of that work. Another one of my favorites, this was found, this IBM punch card was found in one of her notebooks as well. And I think it really kind of illustrates how, in the mid-20th century, there was a real transition between computer being a person's job, like a person's career, and then a transition into, computers as technology, computers as non-human entities, and so I think that is really fascinating and can really kind of be highlighted in a lot of different ways, and with this object in particular. Hoffleit also kind of really loved to keep a lot of items in her notebooks, not just calculations, but also 4-leaf clovers and Christmas cards and a lot of other things that I think really show her personality and show kind of some of the more personal aspects of her life. But of course, she did do tons and tons of calculations in the notebooks that we have, some star charts, as you can see at the top there. And so, you know, of course, there's tons of calculations in her notebooks, but I think the other stuff is really neat too, because it really shows, you know, some other aspects of her life. So these are just some other resources about Dorrit Hoffleit if you are interested in kind of learning more about her. Her papers are kept at the Harvard Archives and the Yale Archives. There was a New York Times article written about her when she died, her obituary. And there's also an oral history of her from the American Institute of Physics. I would highly recommend that one because she really talks about her life at Harvard, at Yale, her work, her research, and I would really recommend that one as well. So thanks so much. And now we'll kind of, you know,